let's do another example. So here we're going to be doing an integral e to the x squared minus y squared dx dy over a region, which I'm going to describe the following way. R is a set of all points where x is less than or equal to y, x is positive, not non-negative, y is non-negative, and x squared plus y squared is equal to 1. So I'll go ahead and draw it. So here we have considered the boundary of this x equals y. And we have that circle, radius 1. And x and y are positive, so region R is right over here. And this is part of the line x equals y. This is part of the circle. Obviously, this is the y symbol. Now I'm just gonna, it's not coming up with a change. Easy to come up with a change variable. I'm just gonna give it to you. We're gonna let u equal x squared minus y squared. And v is 2xy. Which here, instead of having x and y as functions of u and v, we have the other way, right? U and v, the new coordinates, are functions of x and y, the original coordinates. Okay, so in order to compute the, this is, we would have to do a couple things. We have to find what this new region is, r star, in the UV plane. And then we have to figure out what we're integrating, and that's not so hard because x squared minus y squared is u. So we just have to figure out the differential area element in this new coordinate system. So we need to find the derivative. We need to find the Jacobian here. Derivative of x and y in terms of u and v. It's derivative matrix. But that's more difficult, right, if you're not given x and y as a function of u and v. So we can use implicit differentiation, we can use inverse function theorem. So let's just use implicit differentiation. So let's realize what this looks like, right? This is the derivative of x with respect to u. We're going to compute this determinant and take the absolute value. But it looks like we need to compute these derivatives. So let's see if this works out. We're going to differentiate here both sides with respect to, we're going to differentiate both sides of equations 1 and 2 with respect to x, with respect to u and then v. So differentiate equation 1 with respect to u, assuming that x and y are implicitly functions of u. And then differentiate both sides of equation 2 with respect to u. Remembering that x and y are functions of u and v implicitly, so implicit differentiation. Notice this gives me a, we can think of this as a matrix equation. Sorry, this should be derivative of y with respect to this. And likewise, you can differentiate equations 1 and 2 with respect to v next. So differentiate equation 1 with respect to v. Differentiate equation 2 with respect to v. So that could also be written as a matrix equation. Okay, and then we can probably put these together, right? So it's the same matrix here. And then you can have okay, and that's equal to the identity, right? These columns are the columns of an identity matrix. These are inverse matrices. And notice that we don't care about the matrix per se, but much more about the determinant of that matrix. So let's just compute the determinants here. So the determinant of the left is the determinant of the product of two square matrices, so that would be 4x. Determinant of the first matrix times the determinant of the second matrix. And then the right hand side we have the determinant of the identity matrix, which is 1. So the determinant of our matrix is
1 over the distance string. So as long as we're not at the origin, which I guess this makes it a sort of improper integral. Oh, should have thought about it. Should have thought about it. Okay. And we want this to be in terms of u and v. That's a problem. So I'm going to take a little detour here. So we could try to solve for x and y directly as functions of u. Or we can be a little bit more clever and notice that, let's see what u squared minus or plus v squared equals. So here's u being squared, and here's v being squared. So combining these two like terms, we see that we can in fact now factor to x squared plus y squared squared. So this tells me that the square root of u squared plus v squared is x squared plus y squared. So we can think of this determinant as 1 over the square root of u squared plus v squared. Meaning that in our change of variable, the differential area element in the new coordinate system, the UV plane, dA would be the determinant, or the absolute value of the determinant times dU. And I should have had square root over here, unfortunately. No, we're good. I think I could have maybe messed it up, but that's it. All right. All right, so now we have dA. So we just have to now figure out the region of integration, right? So you have e to the u dA. I'm gonna have to redo this one, right? Get a maybe we'll see. All right, so now let's look at the new region of integration as the UV plane. So what we can do is just take it segment by segment. I think let's just focus on that for a time being. Can we get this to move in any? It doesn't like moving. Okay. Legit. All right. Focus on this. So let's just focus on this new region of integration. So let's look at the first segment, the xy plane. Let's look at the segment here. So here we see that we're on the x-axis, so y will be 0, and x will go from 0 to 1. And then let's look at our change variable. Okay, so if y is 0, then u is equal to x squared and v is 0. And as x goes from 0 to 1, then so does u. So v equals 0 is just another way of saying u-axis here. So u will go from 0 to 1 while v is 0. So
let's just make sure we code that. So this segment, the x-axis, maps to itself. Alright, so now let's consider, I guess this segment. This is where y equals x. So now, if y equals x, then you see u would be 0. Now we agree this is 45 degrees. So x would go from 0 to square root of 2 over 2. So would y, but so then if you look at 2 times x times y, so since if you multiply x and y and then also multiply by 2, you would get 2 times half, right? So you get 1. So this means that v goes from 0 to 1. So apparently, this piece here, this segment, maps to, well, u is 0, so we're on the axis, and v goes from 0 to 1. So finally, we can have the third region, or the third segment here. So that's where x squared plus y squared equals 1. So if you'd like, you could always parameterize the segment. You can say that x equals cosine theta, y equals sine theta. And then we look at what u would be then. So u would be x squared minus sine squared. And that we know reduces by a trig identity. So that's going to be cosine of double the angle. Then v would be 2 times cosine sine, which again, by a trig identity, is sine of 2 theta. So here, notice that theta in the xy plane, right, only goes from 0 to pi over 4. So 45 degree angle. So if theta goes from 0 to pi over 4, then we see that 2 theta would go from 0 to pi over 2. So u and v are both parametrized, right? So that green segment becomes a quarter circle in the UV plane. So this is our region of integration. This is our R star. We mapped an eighth of a circle into a quarter circle. All right. So there you go. This is our region of integration.
All right, we're ready to integrate. But I think we need another change of variable, no? You'll probably want to go to polar coordinates. So you probably want to go to the r theta plane and then set integrating over rectangle. So theta is going to go from 0 to pi over 2. R is going to go from 0 to 1. Let's call it r double star, right? It's in the r theta plane. So that becomes u to the u. So u is going to be r cosine. V is going to be r sine. So u to the r theta cosine theta for u. We have, and then we know the differential area element in polar coordinates is r d theta, and then 1 over that is, so the r's cancel. And I don't know if I can actually integrate this or not. No, with respect to r, no problem. With respect to r, the antiderivative is the upper bound. R is 1. Minus at the upper bound. Lower bound, sorry. Or r is 0. So now we have to integrate that with respect to theta. And I don't know if I know how to do that. So I should have thought this through a little better. I should have thought of a better function. Yeah, I'll work on this exam, make it a better example. We should have maybe done that example later. Intriguing. Okay. All right, yet another example. Let's see if we can do this one. We're just going to find an area of a region by integrating over that region, integrating the differential area element. The region R is given. So number 1, in the xy plane, we can draw a region of integration. It's an elliptic disk cut in half by a certain line.
So here are the x-intercepts. So if y is 0, so we get 36, 18. Well, the x-intercept and x-intercepts are plus or minus square root of 18. So 3 times square root of 2. And the y-intercepts are plus or minus 2 times square root of 2. And we have our ellipse. And then we have the line 3y equals 2x. So that's a line of slope 2/3, right? So we can draw a slit with that. And here we're inside the ellipse and below this line. So we're talking about this region as our region of integration. So that's R. So the correct change of variable would be to straighten up this ellipse, right? I could do a elliptic change of variable. So we're gonna let divide by 72 over here. I would probably do something a little different here. Let's first try to, turn this ellipse into a nice circle by letting x equal. So 4 times what is 72, right? So 4 times 18. So we're going to let x equal square root of 18 r goes y is square root of 8 r sine theta. So that way, the equation of the elliptic disk in the xy plane becomes I know this is weird. We're going to let u, or x equals square root of 18 times u, and y equals square root of 8 times v. Let's see why this works. So the equation of the elliptic disk
in the xy plane becomes the equation of a unit circle, a unit disk in the UV plane. So that now we get a nice unit circle in the UV plane. And let's see what that line becomes, right? So you get, see the line in the xy space. That's this equation. We can substitute y and v. So this becomes 6 square root of 2, and this becomes 6 times square root of 2. V equals u. So v equals u is just a diagonal line, right? Although u equals v. And so this must be the new region R star to the UV plane. So you're integrating over a quarter or half circle. Okay. So according to this, this is the integral over R star. According to the change of variable formula, this is the integral over R star. R star, if you'd like, is the set of all points in the UV plane, where u squared plus v squared is equals to 1 unit disk, and u, say v is below u, below that diagonal line. Okay, so then dA, we have to, dA, of course, is the absolute value of the determinant of the Jacobian matrix here. Du dE. The derivative of x with respect to u, with respect to v, the derivative of y with respect to u and v. So this just becomes square root, so 3, 2, 6, 12. All right, so then the dA in the new coordinate distance is 12 times the u dv. And then we realize that this is, since we're integrating over half disk, a unit disk, it should give us half the area of the unit circle. So pi radius squared all divided by 2. So 6 pi. It's not a bad example. So let's do one that has to do with the gamma function, the data function. So this is not an obvious one. So gamma of x is defined like so, as an integral. And Yeah, you integrate out the t, you get a function of s. Okay, now the beta function is a function of two variables. It's defined as the integral from 0 to 1 of, let's just use u, I guess. 1 minus u. This is to the x minus 1, I believe. This is y minus 1. Let's double check. Matter. Right, let's define this to be t to the x minus 1 and then 1 minus t, y minus 1. And these are related, this gamma function and this beta function. So apparently the relationship is itself. So we wish to derive that. So towards that end, we're just going to start with this side, we're going to have gamma of x times gamma of y. And now this gamma of x times gamma of y, you can actually do right as a double integral, of course. Because gamma of x is defined as an integral. And then so is gamma of y. Let's use a different letter, s here. But you can write this as a double integral over the first quadrant of the xy plane. I guess, yeah. No, TS plane, right? So, and then we're just going to combine the exponentials. So notice the region of integration is over some region in the ST plane, namely the whole first quadrant. S and T both go from 0 to infinity. And then proper integral. Here I'm just focusing on change of variables. So it turns out we can cover the same region in a kind of unfamiliar fashion, maybe. what I'm going to do is I'm going to simply take a line here. Okay. And imagine that we have some coordinate called u. U simply tells us how far we go along, and then we have another coordinate. It's going to parameterize the segment given u. So this would be the point. We want to make this the line where the intercepts are u. Yeah. So let's just say this is the point u0, and here we have the point 0u. For some given u. Okay, and then we're going to parameterize this by saying R of t, R of v. Just parameterizing the line segment. So 1 minus v times the starting point plus v times the terminal point. So this is actually a parameterization of the surface in terms of u and v. So we see that x would be 1 minus v times u, y would be v times u. So here we have x and y directly as a function of u and v. So this is the change of variable we're going to attempt. Now notice that x plus y, oops, so there should be s and t, I apologize for that. X and y, s and t. So then s plus t would be, say, u minus vu plus vu. So that's just equal to u. S plus t equals u. All right. Let's go ahead and in reading over some region. Now we can directly replace t with v times u. We can replace s with 1 minus v times u. And then s plus t becomes u. Now we have to compute the differential area element. Oops. The derivative of s with respect to u, with respect to v. Derivative of t with respect to u and v. So this is 1 minus v times u minus negative uv. So this all just becomes du. Yep. After a cancellation, uv minus uv. So let's just do u dv. And now the bounds. So you have to be careful, right? Okay. So v always goes from 0 to 1. Right? So when given u, when v is 0, you're over here, and this v increases to 1, you end up over here. And then you let u go from 0 to infinity, so that way you cover the same first quadrant in a different fashion. So we're going to let u go from 0 to infinity, and v is going to go from 0 to 1. So believe it or not, this is our region R star in the UV plane. So you might want to think about that one. So here v is going to go from 0 to 1, and u is going to go from 0 to infinity. All right. So here I'm going to gather all the u's together. And then gather all the v's over here. And we can have just an integral with respect to v, and then times just an integral with respect to u. And notice that I can, the factors, u to whatever power, you can use properties of exponents. So this is, oops, that's u, my bad. So this becomes u. And we have an extra u, so that just becomes -1. But then you realize that this is by definition of gamma function. So our variable is u instead of t, but this is gamma of x, gamma of y. Now this integral is by definition beta function. This integral is by definition gamma at x plus y. So there you go. All right, and I'll do this over, I suppose.